10,000 nuclear ships by 2050? What do you think? I'm Mark Tipping, the Power to X Director at Lloyd's Register. Recently, we held a webinar where we talked about nuclear in maritime, and today we're going to answer some of those questions that you raised then. Why nuclear in the maritime environment? That's the fundamental question that most people want answered in the first instance. Well, it's not one single answer. There are a range of reasons why you would consider nuclear in the marine environment. The first, and probably most topical, is that it is a true carbon zero technology. It also will be economically viable for many applications as the nuclear in maritime industry develops. But it's not without challenges, and one of those key challenges is going to be to build up a supply chain that enables that economically viable deployment of nuclear power in marine. And we'll talk later about some of those technologies that are being considered for this environment. Nuclear gives us another opportunity, and that is the production of e-fuels in very large quantities. Nuclear being very energy dense means that not only does it take up a small footprint, but we can also integrate it with the e-fuels production plant as well. As we see a multi-fuels approach to maritime in the future to meet net zero, this means we can integrate nuclear in a second way as well, as part of that e-fuels production system.
My name is Jez Sims. I'm the Nuclear Technical Authority, Marine and Offshore at Lloyd's Register. I have 26 years of experience in the submarine service, maintaining, operating and providing assurance for the UK's submarine service. Management of radiation exposure is a fundamental requirement for certification bodies. Previous civil maritime experience from vessels such as the NS Savannah and current naval experience show demonstrable evidence that nuclear and maritime can be operated safely. Proposed new ship designs will utilise advanced shielding using composite materials and those specifically manufactured to reduce radiation to below UK background levels, which is nominally 2 to 3 millisieverts per year. Containment systems that are designed to safely house the reactor and its associated systems will further reduce the risks to ensure safety. When you combine these robust designs and test standards with strict international and national regulations, rigorous crew training and continuous monitoring, the risks can be effectively managed. Breadth and depth of proposed reactor designs, both in technology type and physical size, it does mean there will likely be options for a wide range of deployable possibilities, but it very much depends on the space, power and assets available to determine which technology is best suited. There are a number of technologies being designed, tested and submitted to regulators for approval. There have been over 700 reactors previously deployed in maritime. There's a range of reactor types that can be considered. The most commonly deployed to date is the pressurised water reactor, with a long history of safe operation. Pressurised water reactors provide coolant to the reactor, also serving to slow down the neutrons to maintain the nuclear chain reaction. They have a negative temperature coefficient. That means as the core heats up, the reactivity decreases. This is because the water, acting as a moderator, is less dense. This provides an inherent safety feature. The established operational procedures and mature regulatory understanding mean that it's easy to license. Other designs attracting a lot of interest are the heat pipe microreactor, which is very small by conventional and even defence standards, normally in the low megawatt electric range. Typically, a simplified design requiring far fewer components with a less risk of failure that have embedded heat pipes that passively transfer the heat from the core to the power conversion system. The heat pipes contain a working fluid which evaporates at the hot end, the reactor core, and condenses at the cold end, the power conversion, without the need for pumps. Their size and simplified design and potential operational requirements make them an attractive option for main generator electricity sets. The molten salt reactor can potentially be used with a range of fuel types, but traditionally uranium would be in either solid or molten salt form, which is dissolved into the salt solution. Unlike the pressurised water reactor, the molten salt reactor operates at very near atmospheric pressures, lowering the risk by reducing the stored energy within the system. Molten salt reactors can operate at significantly higher temperatures than pressurized water reactors. This can lead to more efficient power conversion of the heat to electrical energy. If the dissolved fuel is in a salt format, this reduces the chances of a fuel meltdown because unlike solid fuel, the molten salt can be drained into a passively cooled storage tank in certain situations. Lead-fast reactors operate in the fast neutron spectrum, thereby not requiring a moderator. This has the benefit of being able to use different types of fuels, such as MOX, which is a metal oxide, which is already in use in countries such as France and Japan. Lead has excellent heat transfer properties and a very high boiling point, which, like the molten salt reactor, means they can operate at near atmospheric pressures. Because of the high temperatures, they also have good thermal efficiency. High temperature gas reactors use an inert gas such as helium as the coolant. This has the benefit of being not chemically reactive and doesn't become significantly radioactive. High temperature gas reactors, like pressurized water reactors, have a historical operational experience which could make them easier to license and regulate. As before, the operating temperature provides high thermodynamic efficiency. The high temperatures make the high temperature gas reactor specifically suitable for producing high quality process heat for industrial purposes and potentially the production of e-fuels. All of these reactor types have advanced designs which are taking advantage of the inherent benefits of each design: higher temperatures, lower pressures, and passive safety features. However, finding the right fit for the required power production, the operational profile, and of course the economics will mean that not all technologies are suitable for all situations.
So, what are the regulatory challenges for nuclear-powered ships? Well, it's going to depend on the asset type we talk about. Offshore and ship are going to have somewhat different approaches. For the offshore environment, it's going to come under national regulation, which is inevitably going to simplify it considerably. Shipping, on the other hand, does not have that luxury. It's going to need an international approach. And the current regulatory requirements for nuclear-powered ships were developed in the 1970s and don't address the new technologies we're looking at today. So something different is needed. And it's very exciting to see that the International Atomic Energy Agency is putting forward a proposal to look at how we might achieve the international licensing of nuclear in maritime. So what are the first mover projects going to do? Well, very much like has occurred with alternative fuels, with green corridors. We foresee that nuclear corridors will be established. In fact, there's plenty of precedent for this. Nuclear material is already transported around the world and has been for many decades. So we have an existing precedent to work on for this. And indeed, some organisations are starting to look at how this might look as well. So when we look at safety protocols for nuclear ships, we're really talking about safety. And with any of the alternative fuels, it's important that we take a start point, that what we do in the future has got to be at least as safe as what we do today. And that's where I'm going to reference back to what Jez was talking about with the different reactor types and their approaches to passive safety. We should engineer out the failure mechanisms that are of concern to us. And this is our primary line of defence when we're talking about the safety of these assets. Which means we aim to take this to the point where we can shut the reactor down and walk away from it safely and confident that it is not going to harm people or the environment. That is in essence the primary approach. So when we look at what additional protocols would be required, they're likely to be very limited in number. They will be unique to that particular technology. This is something which will actually be easier to achieve than I think most people imagine. And that is because these assets actually pose low-level risk to start with, which means those protocols are likely to be limited in nature. Very necessary, but not as complex as what is being imagined, and will be unique to every reactor technology that is developed.
Security risks are all about preventing unauthorised access to nuclear facilities and materials. This is currently managed by meeting the requirements set out in national design basis threat scenarios. Whilst this still needs to be determined in a maritime context, it will require a security by design approach to ensure the physical security on board, which will include robust cybersecurity. There is also the need for international cooperation on safeguards and the required inspections by national and international Atomic Energy Agency inspectors for accountability.
So we can't really talk about nuclear without also considering those end-of-life products that are generated. That of course goes for the entire energy transition and all fuels. But with nuclear, we need to make sure that right from the beginning we're addressing all of those concerns and the complete supply chain. In fact, no nuclear project will be licensed without a full approach to how it is going to manage these materials through life. Now, when we think specifically about the offshore and the marine environment, it's going to be important to design the assets such that the reactor and end-of-life irradiated products can be removed from the asset easily, allowing the conventional maritime asset to be recycled conventionally. That of course leaves the spent fuel and the reactor, and they will have to be dealt with in a specialist manner. But this isn't a challenge just for the marine industry. This is something the whole nuclear industry has to do as well. So it's a joint initiative. And the advantage of these new technologies and what is embedded in them is that they are required to produce as little material end of life as possible. So actually, the burden of material at the end of life is actually much lower than what we have seen previously with Defence Project or the conventional preceding land-based nuclear projects that have preceded it. So we've come to the end of this session looking at nuclear in maritime. And I want to take us back to where we started with what I introduced. 10,000 nuclear ships by 2050. A large number or a small number? Hopefully we've shaped some of your thinking around that number, and I don't think anybody could give you an exact answer to that at the moment. If you'd like to learn more, LR has done an extensive amount of work looking at nuclear in maritime, and a good start point is LR's Fuel for Thought series, which you can find at lr.org. Thank you very much for your time, and we hope to talk to you soon.